In this video, we'll continue with understanding the structure of an atom and what is an electronic arrangement in an atom. How are the electrons exactly arranged around the nucleus? To understand that, we'll first try to understand what are electromagnetic radiation. So essentially, we are surrounded by electromagnetic radiation. Everything that we use, from starting with like visible light that we see, X-rays, microwave rays, radio waves, all of those are basically part of electromagnetic radiation. This is the entire wavelength or the spectrum of electromagnetic radiation. So this is called the electromagnetic spectrum. What you see right here is called wavelength. Wavelength is essentially electromagnetic radiation can be regarded as waves. So just like how ocean has some waves, if you have waves that are big and small, this distance between the peaks of two waves is called the wavelength of this particular wave. Same is true for electromagnetic spectrum. The distance between these waves, the peaks of these waves, is essentially called the wavelength of this particular radiation. Now, if the wave is really fast, it is high in energy, it's really fast, what would happen? The distance between the peaks is going to reduce. That means that the wavelength will be lesser. So if the wave has high energy, then wavelength is small, and vice versa. Meaning if the wave has less energy, wavelength will be a larger number. Okay, so what you're seeing here as we are going further down in this electromagnetic spectrum, you can see that the wave kind of is going faster. As the wavelength is decreasing, you see here the power exponent is becoming more negative, so which means the wavelength is decreasing. As the wavelength is decreasing, you can see that the waves are becoming closer and closer. That means they are going faster and faster, so they have higher energy. So that's what you see right here. The wavelength is decreasing and energy is increasing. And frequency is essentially the opposite of wavelength. It behaves opposite of wavelength. So as the wavelength is decreasing, the frequency is increasing, and so is the energy. And here you can see in the spectrum there are multiple types of waves: radio waves, microwaves that work in a microwaves, infrared radiation, UV radiation that is present in the sunlight, X-rays, gamma rays. These are all different types of electromagnetic radiation. Now, why are we studying this? Essentially, if we take this portion of the electromagnetic radiation, which is called the visible light, which is called visible because it's visible to us, visible to our eyes, human eyes. If we take this light and pass it through a prism, the prism essentially will diffract this light in a way so that we can see different colors, or it breaks apart this light into different colors. It breaks it into a rainbow, essentially what we call a rainbow. All different colors in the visible light can be seen. Now, if the same light, instead of using the light coming from the sun, if we use light that is coming from an atom, if we heat up an element, let's say, and we pass that through a prism, in that case it will no longer be a rainbow, but it would give you more like a line spectra, where we'll see different lines of different colors being visible to us, something like this. This is referred to as the atomic spectra. So basically each element has its own unique atomic spectra. So each element will produce different color, distinct lines of different colors, and each of these colors would essentially be separated by some darker areas which would look black to us. So this is called the atomic spectrum. And why do atoms produce such kind of spectrum, and why the spectra is distinct or specific towards different atoms? That is because of the arrangement of electrons around the atom. So up until now, we saw that in a structure of atom, an atom consists of a nucleus, which is dense part, which consists of protons and neutrons, and around that we saw there was there would be some electrons. Now these electrons are not just randomly present in any space around the uh, nucleus. They are present at certain energy levels, at specific energy levels, which are called as electron energy levels, or they are also referred to as orbits. Okay, these the energy of the electron is essentially fixed. It is called quantized, which means that electrons can have only specific energy values, which means if let's say this is an atom, if this is an atom, the nucleus is right here. These are the different energy levels that are present around the atom, around the nucleus. So the quantized term essentially means that electrons can only be present at this energy level, or at this energy level, or at this energy level, or here, or here. Basically the colored regions that you are seeing. Electron can be anywhere around in this particular orbit, in this particular energy level. The space that you see between two energy levels, electrons can never be present in this empty space. That space is always going to be empty. And this is what is called as quantized, meaning electrons can only have certain amount of energy. They can never have anything in between. These energy levels are usually referred to by a number which is called the principal quantum number. You can essentially regard this as an address to an electron. So that essentially means if I'm talking about electron, where would that be present, located? What is the exact location where we can find electron in an atom? So this number exactly tells us what is the location of the electron around an atom. For instance, if I say an electron is present in the principal quantum number 1, that means I will basically find the electron somewhere right here. If it is present in n equal to 2, I'll find the electron somewhere right here. So this is essentially telling you the exact location of the electron in an atom. This is also abbreviated with the alphabet N. So, and these basically can go from 1, 2, 3, 4, 5, depending on how many electrons do we have. Another important thing is when you're filling the electrons in an atom, the shell number, this electron orbit or the energy level number 1 always consists of maximum 2 electrons. This can only hold 2 electrons. All the other shells can go up to 8 electrons in total. Okay, now how many electrons does each orbit contain? That would depend on what atom we are talking about. As we know, based on our previous video, we saw that we can figure out how many electrons are present in an atom. So if we know the number of electrons, we can basically distribute atoms around these shells. The only important thing is that we always fill up the first shell that we always fill up is the one that is closest to the nucleus. So you always start filling electrons from closer to the nucleus, and then you go further away from the nucleus. And always the shell number 1 or the orbit number 1 consists of 2 electrons, and then all the following orbits will maximum hold up 8 electrons. So you start filling up shell number 1, then once you have, if you have more electrons, then we move to number 2. If you have more electrons, then you move to number 3. Okay, so let's see, based on this, to give you another example of what exactly quantized mean, just like how, let's say if a person is climbing a ladder, where can we find the person's feet? They would either be on step number 1, which is n equals 1, or step number 2. You cannot find the person's feet hanging anywhere in between these two steps, right? So that means something can be only found at n equal to 1, or step number 2, or step number 3, 4, 5, 6, wherever. So that is exactly what energy levels are. You can only find electrons in either quantum number 1, quantum number 2, 3, 4, but you can never find electrons in between these quantum numbers. So now we were talking about atomic spectrum. What happens? What is atomic spectrum? So essentially what happens when another important thing when we talk about energy levels is that the electrons that are closest to the nucleus have the low energy. So this right here, energy level 1 is the lowest energy. Okay, as we progress away from the nucleus, the energy level increases. So this is high energy, this is higher. As we go farther away, it gets higher and higher in energy. The lowest energy is right here. So when an electron is present in its original location, for instance, let's say some electron was present right here at n equal to 1. It has 2 electrons in this energy level. This electron, when it's present in its original state, is called as its ground state in its original energy level. If we supply any light energy or any form of energy to this electron, what would happen? It would absorb this energy and it would have now excess energy and would get excited and jump out of its original energy level to a different energy level. This right here, the electron, when it is outside of its own energy level, it is called as the excited electron, or the electron is called in an excited state. But at some point, after a little bit of time has passed, this energy will be released and the electron will have to come back to its ground state. This process, when the electron comes back from the higher energy state to a lower energy state, the energy difference that is present between these two states is released, and this is usually released in form of light emission, and that is the color that we can visually see in the atomic spectra. So every time an excited electron comes back to its original state, it produces, whenever it relaxes, it produces some light energy, or it emits light, and that is the reason that we see atomic spectra. And every atom has a very different atomic spectra. That is because when the electron relaxes, its energy levels are its own energy levels, right? And when the electron relaxes, let's say electron had jumped from this energy level, the ground state was N1, and it had jumped to N3. It can jump back directly. There are multiple ways that it can jump back into its ground state. It can directly come back to its original ground state, or it can come back to this state and then it will come back from here to here. Another thing that you can see here, that the space that you see between different energy levels is completely different. For instance, this is a big difference between nucleus and first energy level. The distance between n equal to 1 and n equal to 2 is different than the energy difference between n equal to 2 and n equal to 3. So each energy level, the difference between the different energy levels is completely different. So when something jumps from 2 to 1 or from 3 to 2, even though the jump looks like just one energy level, the amount of energy that is involved in that jump is completely different. Okay? And that's why you see different colors, because each color is a different wavelength, and we saw previously that different wavelengths mean different energy. So a lower wavelength means higher energy, lower wavelength means high energy, high energy means a different color. Okay, and lower wavelength is usually, like, let's say if it's blue, lesser wavelengths are basically starting from violet, and as we go higher in the wavelength, the color changes from violet to red. So as the wavelength changes, the color of the light that is emitted is different, and that's why we see different lines in atomic spectra. Okay, now this is about atom. Now let's see how you can arrange the electrons in an atom. That is called as electronic arrangement. So after this lecture, you should be able to arrange the electrons around an atom, at least for atom until 20. Okay, with atomic number 20, from 1 to 20, you should be able to arrange atoms or the electrons in the different principal quantum numbers. What does that mean? Let's say if I'm talking about hydrogen atom, how many electrons does hydrogen have? It has one proton based on the atomic number 1, so it has one electron as well. Where would that electron be located? It would always be in shell number, or the energy level number 1. Now moving on to helium. Helium has two atoms. sorry, 2 atomic number, meaning it has 2 protons and also 2 electrons, because again it's a neutral atom. So 2 electrons, again, where would they be located? They would also be located in the energy level number 1, because 1 can hold 2 electrons. So if you were to write the electronic arrangement of helium, that would be 2. Now coming to lithium. Lithium is 3 protons, atomic number of 3, so it has 3 protons and 3 electrons. Now if we were to arrange 3 electrons, how would we arrange them? This would be nucleus in the center, then there's energy level 1, which can hold 2 electrons, so I put 2 right here, and then I have 1 more electron left, so I'll put that or place that electron in the third energy level. Therefore the second energy level. That's why you will see for lithium the electronic arrangement is written as 2, 1. So 2 electrons in the first energy level and 1 electron is in the next energy level. Similarly, you can basically write the energy electronic arrangement for all the representative elements starting from 1 to 20. Let's pick another example. Let's say if we are working with sulfur, how would we divide the or distribute the electrons around the atom? So again, if I'm talking with sulfur, sulfur has atomic number of 16. It has 16 protons, so I have to distribute 16 electrons. So I'll start with the nucleus, then I put one energy level, first energy level, can always only have 2 electrons. Second energy level, how many electrons in total? I need 16. So I have 1, 2. I'll start dividing the rest electrons in here. I have 1, 2, 3, 4, 5, 6, 7, 8. That gives me a total of 8 plus 2. 10 electrons. I still have 6 more electrons, so where would they go? They'll go in the next energy level. So this energy level would have 6 electrons now. 1, 2, 3, oops, 3, 4, 5, 6. So essentially you are basically adding or distributing the electrons around the atom in different shells. Always start with the lowest shell at the n equal to 1. It always has 2 electrons, then add to the next shell 8 electrons. If it has 8 or whatever is left goes to the next shell, and if there's still some more left, you go to the next energy level. And that's exactly how you distribute electrons around here. Another interesting thing that you see the period number right here. When we did hydrogen, hydrogen had a nucleus and then the first energy level and 1 electron. Same is true for helium. Helium is this first energy level and then 2 electrons. So what is the outermost energy level for hydrogen? It is, and helium, it is 1, and that is its period number. Okay, how about lithium? We drew lithium right here. So for lithium, what we see, it has nucleus and then 2 electrons and then third electron in n equal to 2. So what is the outermost energy level or orbit for lithium? It is number 2, and that is which period it belongs to. Everything in period 2, the outermost shell or outermost orbit or outermost energy level is going to be 2. The second, n equal to 2. We can take another example. Let's say oxygen. How would we draw oxygen? So oxygen would have 8 electrons. So it has nucleus and then the first shell. I put 2 electrons right here. I still have 6 more electrons to go. So I draw the next shell and I'll fit 6 electrons here. 1, 2, 3, 4, 5, 6. So what is the outermost shell here? The outermost shell is 2, and you can see right here the period number gives you the outermost shell. So what would be the outermost shell in period number 3? Number 3. All these would have third outermost shell. You can see from here they have 3 shells in the outermost in the atom. How about 4? Everything in this 4 period essentially would have outermost shell is going to be 4. You can see it has 4 total number of shells. So period number gives you that information. Okay. Now another important thing right here is all the electrons. If you draw the electron arrangement around an atom, all the electrons in the innermost shells, all the electrons that are present in the outermost shell of an atom are called as its valence electrons. Okay, and what was this that we drew? I think here we drew sulfur. So this is sulfur, this is hydrogen, this is helium, this is oxygen. Let's keep that. So the total electrons, or all the electrons that are present in the outermost energy level of an atom are called as valence electrons. And all the electrons that are present in the other shells, in the inside shells, other than the outermost shell, are referred to as the core electrons. So everything that's inside is called core electrons. So how many core electron does sulfur have? It has 8, 9, 10. 10 of these electrons are core. And how many are valence? It has 1, 2, 3, 4, 5, and it had 6, right? So it should have had 6 electrons. So 1, 2, 3, 4, 5, 6. It has 6 electrons in the outermost shell, so it has 6 valence electrons. How about oxygen? Oxygen we drew was right here. How many valence electrons does oxygen have? Oxygen has 1, 2, 3, 4, 5, 6. Again, it has 6 electrons in the outermost shell, so it has 6 valence electrons. How about lithium? How many valence electrons does lithium have? Lithium has 1 electron in outermost orbit, or outermost shell, or outermost energy level. So it has 1 valence electrons. And why are we talking about these valence electrons? These are the electrons that actually are involved in an electron transfer or electron sharing with other atoms. These are the electrons that are actually involved in preparing or making new compounds, or reacting with other elements, or reacting with other atoms. So that's why valence electrons are very important. This is what makes an element or an atom reactive. Okay, so that's why we care about valence electrons. The electrons that are present in the inside, or the core electrons, are just there, but electrons that are present on the outside is something that makes atom reactive. Another interesting thing that you'll see here is that the number of valence electrons that are present in an atom is actually equal to its group number. So you can see right here, how many valence electrons does hydrogen carry? 1. What is its group number? 1. How many valence electron does lithium carry? 1. What group does it belong to? 1. So the group number essentially tells you how many valence electrons an atom has. Another example you can see is oxygen. How many was in oxygen? The valence electron was 6. Which group does it belong to? Group number 6A. So this belongs to group number 6. How about sulfur? Also 6. Where does it belong? Belongs to group number 6. How about helium? Helium belongs to group number 2. Number of valence electron is 2. You can basically pick any example from here. For instance, let's say if I'm looking for aluminum. Aluminum has how many valence electrons? Based on this, I can say it has 3 valence electrons, right? Outermost shell has 3 valence electrons. Where does it belong? It belongs to group number 3. So the group number essentially tells you the number of valence electrons. Okay, and the period number tells you what is the outermost energy level in an atom. Okay, so therefore these numbers are very important, and it's easy if the question is asking you how many valence electrons does magnesium have. You don't have to solve for its electronic arrangement. You can simply see that it belongs to group number 2. That means it has 2 valence electrons. You can also solve for it and try to distribute the electrons and then confirm your answer or check your answer, but it should come out to be equal to 2 because it belongs to group number 2. And how many shells or how many energy levels would magnesium consist of? It would always consist of 3 energy levels, like you can see right here, 2, 8, 2. Okay, so that is valence electrons and its definition. The last topic we'll cover in this chapter would be periodic trends in the properties of an element. So there will be 3 different properties that we'll be studying in this chapter, and they're periodic trends. So the first property is size of an atom. The size of an atom essentially means the distance that is present between the nucleus of an atom and the outermost orbit that consists of electrons. So not any orbit, we saw the orbit or the energy level that consists of electron, or the farthest most or the outermost electrons that an atom consists of. That is the distance between this, the outermost electron, and its nucleus is called the atomic radius, and that tells us the size of an atom. If we look at the periodic trend, usually the atomic size decreases as we go across a period. Remember, these are periods. As you go across the period, the atomic size decreases. As we go from left to right in a period, the atomic size decreases. And as we go from go down in a group, the atomic size increases. Why is that? We can also, you can think in terms of the outermost electrons, right? As we are going down in the period, this has one energy level, the next one has two energy levels, three energy levels. So the outermost energy level essentially would have this. If hydrogen, it just has one energy level. Then if we talk about lithium, it has two energy levels, so the size is automatically going to increase. When you go to the third shell, it has three orbits, so that means its size is going to be even bigger, right? So that makes sense. As you go down in the group, the atomic size increases, and as we go from left to right in a period, the atomic size decreases. Why is that? Because as you can see, let me uh, pull up this. As I'm going in the group, it makes sense. This is showing you the same thing, that the number of orbits or number of uh, energy levels is increasing, so size is increasing. How about in a period? As I'm going through a period, lithium, beryllium, boron, carbon, oxygen, neon, they all belong to the same period. As you go in the period, what is changing? The number of electrons is increasing, but at the same time, number of protons in the nucleus is also increasing. So the protons are pulling these negatively, protons are positive charge, they are pulling these negatively charged electrons closer to itself, because this has more energy now. The force of attraction between more protons would, higher is the number of charge, would be the more force of attraction would be present. So here the number of protons is increasing, which will pull these electrons closer to itself. So therefore, as we go across in a period, the size decreases. Okay, the next property is called the ionization energy. Ionization energy essentially means the energy that is required to remove the outermost electron from an atom. So if this is an atom, it has nucleus, it has some electrons, let's say here, and then there's another atom which has nucleus, and then the electrons are here, and the outermost electrons are, let's say, in the outer shell. So the energy, these electrons, remember, are attracted towards the protons, and that's what keeps them together or keeps them in their place. So if I want to remove this electron, outermost electron, from its energy level, we have to give a lot of energy to separate this, right? The amount of energy that is needed to separate is called the ionization energy. So if we talk about the trend, as the size of the atom is increasing, it would become easier for us to separate these electron away, because now the distance between the nucleus and the electron is greater, which means it would be attracted towards the nucleus by lesser energy. So I have to use less energy to separate this electron than the electron which is present in shell number 1. If I want to pull the electron from the shell number 1, that would be attracted more strongly towards the nucleus, so I need more energy. So that is why here the ionization energy trend is exactly opposite of size. As the size increases, ionization energy decreases. So therefore ionization energy decreases as we go down in the group, and it increases as we go across the period. So this is the opposite of atomic size. Now the last property is called the metallic character. Metallic character is can be based on what are metals. What is one property of metals? One chemical property of metals is that metals like to lose electrons. Okay, so they like to lose their valence electrons. So any atom which can easily lose its valence electrons will be more metallic. So this is again following a very similar trend. You can basically use the same trend to figure out the metallic character. So this essentially would follow the same trend as the size, because metallic character, just like size, as the size decreases down across the period, the metallic character also decreases, because as the size decreases, it becomes more difficult to take away the electron from the outermost orbit. As the size increases, as we go down in the group, the metallic character also increases, because it becomes, as the size increases, it becomes easier for us to take the electron away from the, or lose the electron from the outermost orbit. So this is how the metallic character behaves. So you can try a few questions based on these trends. For instance, given the elements, if we are comparing carbon, nitrogen, fluorine, which of these atoms is the largest atom? So which one has the highest atomic size? So again, you will look at the periodic table. Atomic size, you know, as it goes down, the atomic size increases, and as it goes from left to right, the atomic size decreases. So we'll use this trend and compare these elements in the periodic table. And if you look at this, based on this, the size that will come to be the largest one would come out to be carbon, because uh, carbon lies right here, carbon, and then this is oxygen right here, nitrogen is right here, and fluorine is right here. So as we are going this way, the size is decreasing. So oxygen has a smaller size, fluorine has a smaller size, and nitrogen, as we go this way, size is increasing. But because the size is already decreased this way, oxygen and nitrogen would be still smaller than carbon. So carbon is lying more towards the left. So carbon would be larger in size. Similarly, we can talk about ionization energy. So whichever one, remember ionization energy, exact opposite of size. So if in based on this rule, fluorine would have the highest ionization energy. Now the easy question is, which belongs to group number 5a or 15? The element that belongs to group number 5, carbon, is in group number 4, oxygen is in group number 5, and the atom that we are looking for in group number 5 is nitrogen. So again, all this information, you don't have to memorize it. The periodic table you would have up in front of you, so you can just look at the periodic table and figure out the answer. But periodic trends is something that you should try to memorize. There are some more questions for you guys, so you can practice those on your own and let me know if you have any questions. And that is the end of this chapter. If you see any extra information in your book, any extra sections in your book, for instance, I think there's some Lewis structure in here, we'll be covering those in the next chapter and skipping that in this particular chapter.